Continuing on with class 13, here's another example. It's a problem out of the Borgnakke chapter 4, where we have a 0.6 meter diameter household fan. It seems kind of large. Takes air, I guess that's too bad. What was that, like 2 feet? Yeah, something like that. Air in at 98 kilopascals, 20 degrees Celsius, and delivers it at 105 kilopascals, so just a little bit larger pressure. 20.4 degrees Celsius with the velocity of 1.5 meters per second. And there's a picture of a fan in case you need to know what a fan looked like. What are the mass flow rate, kilograms per second, the inlet velocity, and the outgoing volume flow rate in cubic meters per second? Boom. Okay, well, do I want to write down everything? Maybe I'll start with the area. Pi over 4 d squared. So pi over 4, 0.6 squared is 0.2827 cubic square meters. I almost said cubic meters. Almost messed up. I want to get the specific volume probably before and after. So I'm going to go to table A.5 and find R of air, which we should probably have memorized pretty much because we keep looking it up. And then we can use the ideal gas law, P little v equals RT. And we can find our V1 by taking RT1, dividing it by P1, or 0.287. See, I'm going to drop the other thing. And I'll make sure we do 293, and divided by the 98 kPa. See, I didn't multiply that by 1,000 and that by 1,000 this time. I can be flexible sometimes. I don't know. Maybe it's a bad thing to give it up at this point. 0.8581 cubic meters per kilogram. Whereas V2 are T2, P2, 0.287 times. And now the temperature, just a little tiny bit. 293.4. Great. And 105. Not a big change, not a big difference. 0.8020 cubic meters per kilogram. Great. All right, so now something we could find pretty easily. I don't know it's even kind of the last thing they asked for. It was the outgoing flow rate. We can multiply the velocity times the area. Right? Velocity times area is the volume flow rate, and we were given the volume right here, so we could get the velocity. Excuse me. So you get 1.5 meters per second times the area. All right, so that was something we could have calculated this before. 0.2827. So from that, we get 0.4241 cubic meters per second. All right. And from that, we can find what the mass flow rate is, because all we need to do is to divide by the specific volume. So we had 0.4241 divide by specific volume here, 0.8020, and we have 0.5289 kilograms per second. And we could find out what our initial volume flow rate is going to be. So V1, because the this mass has to be the same. It's not mass 1 or 2. It's, conservation of mass. So the mass in has to be equal to mass out. So this is both mass in and mass out. So just mass flow rate. So we could take that mass flow rate and multiply it by V1, and that will give us the volume flow rate in the beginning. So 0.5289, and now multiply it by 0.8581, and you get 0.4539 cubic meters per second. And now if you want to find what the velocity is, we can just take, we know that 1 is going to be the velocity 1 times the area 1. So we can find what the velocity 1 by dividing the flow rate, volumetric flow rate, by the area. Is that true? Sure. And the area stays the same. Well, we're assuming that, right? There's no like nozzle thing around it, so the inlet area is different than the outlet area. 0.4539 we just found, divided by 2.2857. So 1.605. And this is sort of a surprising thing. The volume, the velocity coming in is actually larger than the velocity going out. But the pressure is larger on the way out. I would mention that there's some fluid mechanics things that we might want to be talking about in this, but this is really just messing around with flow rates, mass flow rates and volumetric flow rates and velocities and areas. Just an example of using those to try to get used to them. We should write down all the answers right here. So the first answer was the mass flow rate. And so 0.529 kilograms per second. The second part of it was asking for the inlet velocity. So that's like actually the last thing that we found. 1.61 meters per second. And then the last part of it was asking for the outgoing flow rate, or V dot, naval architecture V dot 2. And that was like one of the first things we calculated, 0.424 up here, cubic meters per second. And we will go to another video. I'm not sure I'm going to be able to record all these videos. I made a lot of examples. Oh, no, this is the next class, class number 14. Boy, do I have a lot of examples.